Welcome back to Zero at Math. Here's a classic limit that looks completely obvious at first glance, but let's prove it rigorously and see why it's true. We want the limit, as x approaches infinity, of the natural log of x divided by x. In other words, the limit as x goes to infinity of ln of x over x. Most people intuitively say zero, because logarithms grow very slowly and x grows without bound. But how do we actually prove it? We'll do this completely analytically. No graphs, just pure algebra and inequalities. The strategy, L'Hopital rule, quick and clean. Since as x goes to infinity, ln of x also goes to infinity, this is an infinity over infinity indeterminate form. Perfect setup for L'Hopital rule. L'Hopital rule says, if the limit of f of x over g of x is an indeterminate form, like 0 over 0 or infinity over infinity, then the limit equals the limit of f prime of x over g prime of x, provided that limit exists. Here, f of x is ln of x, so f prime of x is 1 over x. And g of x is x, so g prime of x is 1. So the limit becomes the limit of 1 over x divided by 1, which is just the limit of 1 over x. And that is clearly 0. Done. The limit is exactly 0. But maybe you want a proof without calculus, no derivatives at all. Let's do that too. We will use logarithm properties and a simple inequality argument. First, for x greater than 1, choose an integer, n such that 2 to the n is less than or equal to x, and x is strictly less than 2 to the n plus 1. Then the natural log of x is strictly less than the natural log of 2 to the n plus 1, which equals n plus 1 times the natural log of 2. Meanwhile, x is at least 2 to the n. Putting these together, the ratio ln of x over x is less than n plus 1 times the natural log of 2 all over 2 to the n. Now, as n grows, the denominator 2 to the n grows exponentially, while the numerator n plus 1 grows only linearly. So the fraction goes to 0. In symbols, n plus 1 over 2 to the n tends to 0 as n goes to infinity. Therefore, by squeezing, ln of x over x goes to 0 as x goes to infinity. Either way, whether you use L'Hopital rule or this elementary bounding argument, the limit is definitively 0. Logarithms, no matter how slowly they grow, are completely dwarfed by a linear term in the denominator as x goes to infinity. There you have it, a clean, rigorous proof that the limit is 0. If this kind of limit analysis excites you, like the video, subscribe to Zero at Math for more classic limits and elegant proofs. See you in the next one.